Hi everyone, welcome back to Algorithm Simplified. This week we are going over number 305, number of islands 2. This is a hard level question in particular that uses UnionFind data structure as its solution. And it's definitely a prerequisite for this video that you understand at least what the UnionFind data structure is. So if you don't know what that is, I've provided a very useful summary video at the top of the description. So if you'd like to check that out before continuing this video, that would be the best option. And also recommended is that you at least try number 200, number of islands, since that is the prerequisite to this question right here. Okay, without further ado, let's get into the problem itself. So basically, this is what you're given. You're given 3 variables. 2 of them are integers, representing a dimension of a grid. The other is a series of, or an array of arrays. Each of these subarrays are 2 long, each one with its own integer coordinate between 0 and m and 0 and n accordingly. I write them as ij, which represent some coordinate in the grid. Let's illustrate what this means in an example. So let's say you're given m equals 3 and n equals 3. This means you start off with a 3 by 3 grid, like so. And to start off with, all plots of your grid are going to be 0, where every single 0 represents water and 1 represents land. So this is where you start with. Okay, so afterwards, after you start, for every single position in position, starting from the 0th index all the way till the last, we go step by step, adding the land at position ij in positions to our grid. So what does that look like? For index 0, we start with that. So that means at 0, 0, we're going to update that into 1. And everything else remains the same. This means at 0, 0, we add a plot of land. Continuing forward. Okay, pretend that's also 3, 3. 0, 1, so that's going to be right here. That's going to become a 1. Everything else remains the same as the previous state, and the 1 carries over from here. So this is index 0, this is index 1. And then here for index 2, I'm just going to do, so this is 1, and this is 2. So right here, that's going to be updated to a 1. Everything else carries over from before. And this is the state of our grid after index 2 of positions. And then following that, for the last position update, we're going to change the 1 at position 2, 1 into 1 as well. So everything else remains the same. And all these get updated to 0. Right, so what the question asks, so what you're expected to give as an output is an array of integers of the length of position. So let's call this result. So we're supposed to return an array with here, 4 items, each one representing the state of the grid in the corresponding index. So for example, here, this points to this grid, here, this points to this grid. And what exactly we have to have in this result array is the number of islands. And we define the number of islands as the number of ones that are, or number of groups of ones that are completely surrounded by water horizontally and vertically. So what this means is, for example, here, this right here is 1 island because it is either surrounded by all zeros, it's surrounded by 0 vertically and zeros horizontally, or it's out of bounds. Out of bounds, we also considered water. So that is a proper island on its own. There's 1 island right there. Here, we have 2 ones connected together horizontally. So, and they are all vertically and horizontally neighboring water on the outside. So these ones right here are considered 1 island on their own. So that's 1 island. And here in index 2, we have 1 island here, but since this right here, even though it's diagonally connected, it's not horizontally or vertically connected. So this right here is a separate island on its own. So we have 1 island here, 2 islands here. And finally, for this last one, we have one island here, horizontally connected, one island here, and also one island here that's also on its own because vertically and horizontally, it's surrounded by zeros or out of bounds. So we have 3 islands. And in the end, we're going to return this. So our task is to, given m, n dimensions, and also these positions in the m by n grid, we're supposed to return an array of length of positions that gives us the number of islands present at every single position corresponding to the result array index. Before we head into the solution, here's something we need to consider. So in number of islands 1, the predecessor to this question 305, one of the ways we could have solved it was using either BFS or DFS. In fact, I believe in that prior question, BFS and DFS were actually quicker and better solutions. However, in our case, can we do that? Well, let's consider this case. So let's consider that we have at some position I, this following scenario in our grid. So we have 1, 2, 3, 4 islands separate from each other, all surrounded by water horizontally and vertically. So here we have number of islands equals 4. But let's say in position I plus 1, we're tasked to add a plot of land or change a 0 to 1 at position 1, 1. Then what happens? Well, now all these plots of land are connected horizontally and vertically together, meaning we decreased our number of islands from 4 to 1, meaning we decreased our total number of islands by 3 using 1 island. This means that because we cannot strictly increase or remain the same with the number of islands as the positions change or as we increase the number of land plots added in, we can't use BFS or DFS as the number of total islands can range anywhere from decreasing in 3 all the way till increasing in 1. It could be anywhere in between. So this means no, or let's switch, no. We cannot use BFS or DFS, but instead we have to use UnionFind. And while UnionFind is definitely an accepted way to go, in this solution video, I'm going to discuss UnionFind implemented with rank and path compression, which is going to give us a much more efficient, time-wise solution and implementation of UnionFind. Now let's see how we would solve this problem using UnionFind with rank and path compression. So the basic idea here is that we're going to treat each ij node or each ij in the grid as a node in some graphs. In particular, those graphs are going to be trees. Each tree is going to be an island. So if you can imagine a root representative node as the parent, the root parent of everyone else in the tree, that would be one island right there. And each island has one distinctive root or node representative. So if the island just consists of one plot of land, it's just going to be one node. So using the same example, I'm going to walk through the algorithm and the implementation. So first, we initialize some variables. We initialize parents to be an array of size m by n and all containing -1 to start. The parent of some grid position, so of some node, is -1 if it's an ocean. And to start, we have an n by n grid of only ocean plots, so all -1s make sense. Rank refer to the position or how close a certain node is to the top of a tree. So if we had a tree like so, the rank of this node will be greater than the rank of this node. We're also going to initialize a count to be 0. This is going to count how many islands we have at one time. And then find and union methods are the same as you would expect from any other UnionFind data structure, except with our finds implementation, we're going to use path compress. So we're not going to care, that we're going to hold exactly the parent above. So let's say we had something like this. In compression, the parent of this node right here is ultimately going to be compressed to this node right here, even though the direct parent is this. So you'll see what I mean as I go through that. And then in union, we're going to compare ranks to make our algorithm go faster. And we also initialize a result array with the length of positions, which holds in accordance to every single positional update how many islands we have at that very instance. And also to note, when I refer to ID, that's UnionFind or find, ID of some ij in the grid is calculated by I times n plus j. And this makes sense because if you have, say, an m by n matrix like so with x and y axes, or it could be the other way around, and we have some ij right here, basically think about it as, well, we're going to have how many columns over? Well, we're going to have I columns over because that's the x-axis, right? And each column is of length n, so that's I times n. And within this column, I times n right here, we're going to have to move j up in order to reach ij. So if you do the other way and do j times m plus I, that's also a valid way to calculate the ID, though the ID values will be flipped the other way around. So just as long as you have one consistent way to hold your ID, either way works. Okay, so let's run through our example right here. So what we're going to do is we're going to loop through every single position and perform the following. So first, let's start with our first position, and that is 0, 0 right here. And let's calculate what that ID would be. So that ID of 0, 0 would be 0 times n, which is 0, plus 0 is equal to 0. Okay, so first, we plus 1 to the count if the ocean is at our current 0, 0 position. Well, at index 0, accordingly, we could see that parents is -1, meaning that right there, that plot is ocean. And this makes sense because we start off with an ocean-only grid. So we plus 1 to the count, since we added one plot of land. Then we update the parent's ID equals the current ID if it's at the ocean. And it indeed is. So we update it to be 0. As you can see, as I said before, any position or any index in parents that is ocean is going to be -1. But anything else is going to have a non-1 value, meaning it's a piece of land. So here, 0 pointing to itself as its own parent means 0 is the representative root for its island. And this makes sense because right now our island looks like this, with one node and no children. Okay. So for left, up, right, and down neighbors, so as we can see, above 0, 0, it's out of bounds, so we don't care. Left is also out of bounds. Right and down are both within bounds, but they are all ocean zeros, which means we're not going to union with anyone because there is no land beside it, neighboring it horizontally and vertically to union with. So we skip this part. And then finally, we're going to update the result at our current index, which here we are at index 0 in positions, to be the current count. So we are going to have 1 right here. Great. Now we're going to loop through this again, and I'm going to go a little faster because hopefully you understand what I'm doing now. So now we're here at index 1 in positions with position 0, 1. The ID for position 0, 1 would be equal to 0 plus 1, which is equal to 1. And then we're going to plus 1 if at the ocean, and indeed it is at the ocean because it's a -1 in the parents, so we're going to add 1 to our count to make it 2. And we're going to update the parent's ID if it is an ocean. So yes, it indeed is an ocean. We're going to update its ID to be its own representative node. And then for left, up, right, and down, we're going to see if any one of them is a land plot within bounds. And indeed, we do see that 0, 0 is. Why? Because at 0, 0's respective ID, which is index 0, we have a non-1 parent, meaning that 0, 0, its neighbor, is a plot of land. So what this means is we need to use union. So what union does is, using find, it finds a root ID of the 2, and that's very easy because we reach 0 and 1 right away, itself right away. So those are its own roots. So then we use the rank to establish who should be the parent over the other. Well, since right now for 0 and 1 accordingly, they're both of equal rank, 0, 0, that makes sense because both of them are root nodes themselves to their own respective islands as of right now. So we're going to make one have greater rank and then thus make that greater rank the parent node. So in this case, you could do this either way, or I'm just going to make 0 the parent node. So that means it's going to look something like 0 is this, and then its child is 1. So that's one island. And then I also need to update the rank. So now we need to plus 1 to index 0's current rank to show that it has higher or closer to the root node than any other node. So 1 is greater than 0 now. And since this union was successful, so we did indeed find a union to merge this land onto, then we need to subtract our counter by 1. And since for the other 3 positions in next to 0, 1, we have no other land plots, then we continue on. As you can see, we're going to update in position 1 our current count 1. All right, next over, we're looking at 1, 2 right here. So what's the ID of 1, 2? The ID of 1, 2 is 1 times n, which is 3 plus 2 equals 5. So first, we're going to plus 1 count if the ocean is at our position. Well, the ocean is at the position 5 right here, so we got to add 1. Now see if, say, we were at 0, 1 again, then we shouldn't add this 1 because 0, 1 is already a piece of land that was considered. So that check right there is to make sure that no duplicate land adds occur. Okay. And now we update the parent's ID to itself since it is an ocean. So we make this 5 to represent the 1, 2's respective ID. And then for up, down, left, and right, we check if any neighbors are land. Well, up, down, left, right of 1, 2, as of right now, there are no lands. They're all -1 for parents. So we don't change anything to the total count. And we just add the count to index 2. Next over, we are going to look at 2, 1 right here. So ID of 2, 1 is going to be 3 times 2 equals 6 plus 1, which is equal to 7. So at 7, you see that it is -1. That's an ocean plot, which means we have to count one more piece of land. And then we also update itself to represent the fact that it's its own piece of land so far. And then we're going to go up, down, left, right to confirm if it does indeed have any land neighbors. No, it does not. So we don't union anything. And then finally, for the result, we just update to our current count. And now that we're finished, we return the result. So right before I head into the coding part of the solution, if you've made it to this far in the video and you like the content you see, please do consider subscribing and liking the video so that I can make better content for you. Now, without further ado, the coding solution. Now I'm going to code out the solution in Java, and I'm going to give detailed comments as we go along, and also give the time complexity at the very end. Even though it's in Java, the same logic follows for any other language, so you can follow along no matter which language you're coding in. So first, let's get the logic down for the for loop, or basically what we're going to try to do. So first, we're going to instantiate an instance of UnionFind, which we will declare later. And it's going to take in the parameters m and n. Then what we're going to do is, well, for the sake of simplicity, I'm going to have a variable that's going to be representing the length of positions so that I can instantiate a result array. I'll make it an array list with length p. Then afterwards, we're going to use the same for loop logic as discussed previously. So for some index starting from 0, looping throughout all of the positions we are given, we are going to add the element x corresponding to the positions. We're going to add the result of something we're going to call place. Now this is going to be a method we're going to write inside the UnionFind, but you can also break it down here. It really doesn't matter, but the implementation is up to you. And then we're going to return result at the end. Great, so that's the basic logic for what we're going to do. But the hard part is that we actually have to define the UnionFind class. So what we're gonna do is, let's write class UnionFind. And it's going to have the following variables. It's going to hold parents. It's going to hold the rank. It's going to hold the count. And it's going to have m and n, the dimensions of the grid. And now for every instance we create, it's going to take the m of the grid. It's going to take the n of the grid. And what it's going to do is we're going to set m and n accordingly. And then we're going to make parents instantiated to be the size of m times n. And we're going to do the same thing for rank. And remember that since in our implementation we make parents all -1, what we do is we're going to iterate through parents. So we're going to make each one instantiate to -1 so that index 0 and default value 0, which Java instantiates it to, are not mixed up. So parents I equals -1. And note for any other languages, rank is going to be instantiated with all 0 values. So if you're in a language that needs to indicate what it's instantiated to, instantiate it to 0. Okay, so that's I'm gonna find, great. So now what I'm gonna do is I'm gonna define methods. We're gonna need one method called find. That's going to give us so if we give it the position index, it's going to give us the index of the root of the tree in return. And we're also going to have a void, so something that doesn't return anything, called union, which is going to take in 2 IDs. And in the end, it's going to union the 2 lands with rank. And then for the place method that we've defined right here, what it's going to do is it's going to return the current count given a specific position ij. So let's get to writing these functions. So for find, what we're going to do is we're going to use path compression. So how do we know if we've reached the end of the tree, as in we've reached the root representative? Well, if the parents of the current position we are looking at is equal to its current position, that means we're at the root. But in order to compress it, what we're going to do is we're going to check if it is not equal to the position index. In other words, we're still in a child node. We're not at the very representative root node yet. What we're going to do is we're going to make the parents of this current index we're looking at equal to find parents position index. And what this does right here is next time we search for the parents of the position index, or we're trying to find the root of the position index, we don't need to go all the way up. It's parents, so on and so forth, all the way till we reach the top. All we're going to have to do next time we try to find the root of some index we previously searched is we're going to be able to directly access the very root node. So then at the end, if it's the case that we've reached the top, then we simply just return parents position index, right? And now what we're gonna do with union is that, well, we're gonna leverage the find method that we've defined here to find the root IDs of these two, ID1 and ID2. So int root index 1 is equal to find ID1, and then int root index 2 is equal to find ID2. And now the thing is, if ID1 and ID2, so these two pieces of land nodes, end up being part of the same island, so ultimately meaning root index 1 and root index 2 are the same, then we don't do anything. we only bother merging them together or unioning them together if they're not part of the same island already. So if root index 1 does not equal root index 2, then we do something. So what we're going to do here is use rank in order to make our algorithm more efficient. If we didn't use rank, well, we could have simply just made any random one, well, it could have been 1, it could have been 2, over the parent of the other, forming ultimately one bigger tree with one subtree from the previous island. But instead, what we're going to do is we're going to use the checking of the rank. So if it's the case that the rank of root index 1 is greater than the rank of root index 2, meaning that root index 1 has more children than root index 2, or more depth of children, higher, more height in island tree than the tree of root index 2, then we make the parents of root index 2 equal to root index 1. So in other words, whichever root index node ends up having a greater height for the tree it's connected to is going to be the parent. And here, else if rank of root index 2 is greater than the rank of root index 1. So what if it's the other way around? Then we're simply going to flip it the other way around. So we're going to make parents of root index 1 equal to root index 2. But what if it's the case that both of them are equal? And this could be very likely. If they both have the same depth or height for their connected trees. So then what's going to happen is we're going to just make any one of them the parent over the other. But whoever is made the parent has to have their ranks changed accordingly. And then, since the root index 1 and root index 2 have successfully been merged into or union into the same island, we're going to decrease the count of the islands by 1. Well, why does this rank make sense? Well, this rank check is very important for making sure that our binary trees are as short as it can possibly be. Because the higher the rank is, the more layers or more heights we have after this root node. So if we somehow always happens to be that we make an insanely long height tree from one node with a really high rank, instead of balancing it out on either ends, then we will have a very inefficient find algorithm. So the rank is very important to shorten the time needed for find. Okay, so what would place look like? Well, place leverages both find and union together. So let's write it out. I'm going to define int I as just the position 0 of our given position, and int j as position 1 for ease. And basically, if we have yet to encounter this ij land node, then we first add 1 to the new island count and set the land node to its own parent to start. So what this looks like is simply if parents of I times n plus j, remember our formula for the ID, is equal to -1, that means it's currently an ocean plot right now. We're going to increase the count by 1, and then we're also going to set itself to be its own parent because it represents its own island representative node to start with. But afterwards, what we're going to do is we're going to compare it with all up, down, left, right neighbors to see if it actually, we need to union and update parents and also update count. What I'm going to do is I'm going to define some directions in which the land nodes can be connected. What that would look like is int array of array directions is equal to So we can go 1, 0, meaning we can go to the right. We can also go to the left. We can also go up, and we can also go down. Now you don't necessarily have to define this array of arrays. I just find that it's easier for me to understand because in this for loop right here, what I do is for each direction, in directions, I create, or I name I2 and I2 and J2 as the variables for I and J of the new direction. So I2 equals I plus direction 0, and J2 equals J plus direction 1. And then right here, we're going to check if there are any adjacent land nodes. And if yes, we join the lands. So if our I2 is within bounds, so less than m and is greater than or equal to 0, and our J2 is also within bounds, because remember, anything outside of bounds is automatically considered ocean. So greater than or equal to 0. And making sure that if it's the case that those checks have passed, the parents of this I2, J2 is not equal to -1, meaning that it's a land node. So if that's the case, then we're going to union the I times n plus j, so the position we're currently on, with its neighbor that we're looking at. So I2 times n plus j, 2. Okay. So that's our algorithm right now, and let's give it a submit. And great, we're faster than 90% and less than 56% of memory.